Okay, let's get this show on the road. Sorry about the late start. I wanted to make absolutely sure that we had audio in the screencast this time. All right, so to begin with, who loves Rob? Nice, that's great. It's good. So we don't need more Rob, I guess, if everyone already sufficiently loves it. All right, so first up, let's cover kind of the results from homework 7. We're at this point at 65 students plus one auditor in this course, of which 60 attempted the last homework. So if you haven't attempted the last homework, that's bad news if you're in the course. It's a little strange. So I don't know if you have. I'm always happy to talk. I prefer you don't just silently fail. Out of those, as usual, the curve kind of acted exactly counter to the original design, and it just boosted people up past a certain point. We had 38 A pluses, 1 C, and 21 E's, out of which some were 0 points. So that's also a little concerning. The grading system of the course continues to get more and more complex, so we're approaching some Turing completion here probably. Basically, the worst case grading system is what is in the original syllabus. Every other tweak has been done in a way that it has no chance of hurting your grade. So with every tweak, there's always a maximum of pre-tweak grade and post-tweak grade applied. So I figured I'd summarize the tweaks here. To begin with, we started tweaking things heavily in homework 5, where the homework 5 grade is actually the maximum. Oh wait, that's incorrect. Hold on, let me fix that so that we're all.
So I noticed Connor still hasn't sent us our grades then.
So Connor's supposed to have sent you your grades.
I was busy at home.
Hold on, let me restart this.
The grading system continues to get more complicated. Some of which I hadn't realized existed. I realized number 3 was a thing.
Okay, so here's the first thing is homework 5 was you could not do worse than your average on homeworks 3 and 4. Homework 7 would count for 2 homeworks if it raised your grade, otherwise 1. So that's the thing that I mentioned last week or in an email. Basically, the original plan was to cover 3 different topics. So if ROP was just not your slice of pie, then you could work on other things. But that did not happen. And so, again, error in your favor. We'll compress it down to 1 for those for whom it would hurt. Then, I mentioned this weeks ago, I think offhandedly during a class, but it seems that this wasn't propagated properly. Basically, the curve right now, the original intended effect was that, getting 71 points would possibly still keep you at 70 even, depending on how everyone was doing. And that's what we saw when we were in homeworks 1 and 2. In homeworks 1 and 2, you have to get really high in order to get that A+. Now, just getting 71 immediately boosts you to the A+. So our homeworks become pass-fail in some way. So that wasn't the intention with the original grading system. To work around the frustrating situation of, okay, if I had solved one more thing and got a 71, then I would have an A+, but instead I have a 69 and a D+. I agree that doesn't make much sense. So the grade that you will get per homework is after homework 2, because 1 and 2 had potentially thousands of possible points, so this wouldn't really help. Your grades are the maximum of either your curved grade, so that you hit the curve and you got boosted directly to that A+, or the ratio of things you solved to things that were available, right? So hopefully that will help mitigate the situation where you're almost at the curve, but not quite. On top of that, I mentioned this a while back, the lowest homework will be dropped. That will happen as the second to last action in the grading system. And then the last action, conversion of your grades to the actual final grade. At some point, I think on homework 3 or something, I said we're shifting the cutoffs a little earlier, a little lower. So an 87 will get you an A- as opposed to a 90. Any questions on this?
So in number 3, it's supposed to be earned points divided by total points, right?
Thank you.
No, don't correct that. Connor, it won't that one.
That's funny.
The first one is, yeah, everyone will get
But it will
Okay.
soon here.
Let's represent this.
As soon as I figure out how to do it.
All right, any other questions?
Just out of curiosity, does 4 and 2 combined mean that you could just drop both homework 7 grades?
Yes. Yes, so the original concept with homework 7 was tons of 3 different exploitation concepts. That didn't happen. Originally, I was very firm that you won't be able to drop both of them, but we will try to work with you on whatever. I mean, the fundamental philosophy that I've developed as I've been teaching this course is originally I wanted you all to compete to be, the very best hackers. We have some amazing hackers developing here. I've been very impressed. But in the end, it's, so many people are learning, and they're learning sufficient to the point where I don't feel that they should be failing. And, we're trying to make sure that there's a nice objective criteria that works for everybody, where the people deserving to pass should, of course, pass. Any other questions on this?
Maybe this is on the next slide or something, but what are your plans for the remainder of the semester regarding homework?
Right, so I actually need a show of hands from you. So we have one class that is Wednesday night before Thanksgiving. Who will be here? Okay, and who will not be here? Okay, so for the most part, we'll be here. Okay, cool. So the plan is, so we have this week, we have a homework, and then we have 2 other classes plus Thanksgiving. So, plus the final. So the final is going to be a take-home final assigned on the last week of class that will be in the format of an SSH endpoint that you'll SSH in, choose a binary or a program or however that is, and get a flag for solving it. Submit that flag. Sound familiar? Okay, so we'll have this homework, and we'll for sure have 2 more homework, counting the final as 1, right? So, what to do about Thanksgiving? I'm kind of torn about that. So one possibility is no homework for Thanksgiving.
Thanks. I want to go and spend time with my family.
Yeah, family.
I know.
Yeah.
This will be
We could also have a homework. Maybe what we should have for Thanksgiving is a make-up homework. Similar to homework 4.
Yes. Don't do that for all of the binaries.
I think let's do that for Thanksgiving. So for Thanksgiving, we'll have a make-up homework for those that need it. All right.
So then, given that we do the next two homeworks and we get a grade that we are okay with, you can just not do the final homework and that'll be the homework that gets dropped? Like the take-home final?
Yes.
Okay.
The final will be subject to the lowest homework grade drop. So, hopefully, we will have an email out to all of you with your grades. And then,
Figure out the order of operations. on how
that's
that
right.
works.
There's a bit of implementation work, and then you can make your decisions on how to proceed.
Just curious, would the final be cumulative?
So the homework for the Thanksgiving, let's say, will be cumulative. The final, I think, will be, depending, a lot of this, there are problems with actually like building out all of these assignments.
Right.
So one cool thing would be cumulative in the sense that there are complex systems where you need to use combinations of these vulnerabilities.
Right.
That's my dream goal. If it turns out we don't have enough time, you'll explore one additional concept instead.
So what concepts are we going to explore for sure?
So for sure, so this week we will, and I apologize about this, I thought we could do format string vulnerabilities as an aside for things that hasn't been working. We will spend this time on format strings. I know you're sick of seeing them, but we'll finish those next week. Heap exploitation, the week, and then we have 2 weeks. So Thanksgiving, for class, we will cover a concept, and maybe Thanksgiving and the last week we will do kind of other advanced exploitation scenarios, type confusion, serialization, things like this. So, any other questions? Duffy?
So does number 4 apply to the final?
Yes. Yeah, so if you're acing the course and you just want to be done with it, that's fine. Oh, that keep spraying. Keep spraying? Yeah, sure. Heap spraying we can do. What else?
The makeup's gonna have the same kind of rule as number 5, right? Where it's just okay.
Yeah, makeup will just be an average of all the previous ones. All right, going once.
Did you say that last? What did you say?
The makeup homework will just be a normal homework in the sense that it is a single homework. The same number 3 applies to it, and then something very similar to number 1 will apply to it, where it is the maximum of all the previous ones and the final one. All of this being said, like I mentioned, all of these changes have zero way to hurt your grade, right? But if you feel that this is confusing and you would like to simply have just the original syllabus framework applied to your grade specifically, you can tell us and we will do that.
Just one last iteration, just to confirm. There are 3 homeworks left, including the makeup.
No, 4.
4?
Yes. There's this week's, then the 14th, then the makeup,
Okay.
and then the final.
Okay. Thank you.
Correct. Out of those, if you're acing the course, and you have no homework so far that you want to drop, you do 2. All right. Anything else? But I would, of course, strategically speaking, I'd recommend to leave the final for the one you don't do, just in case something goes wrong, and you've already used your drop one.
So homework 5, if we didn't do homework 5, that's not being counted for the lowest grade drop. I'm just
Correct.
making sure.
Yeah, yeah.
I don't
Homework
want to
5,
I don't want to be crazy for something.
Yes,
Okay.
the grade of homework 5 is, Connor's looking at this one.
What's the order of number 2 and 4? What takes precedence?
2, 4.
Oh, we already covered that. 2 and 4.
Or is it more like try everything, take the highest grade?
Yes, let's try everything and take the highest grade.
I already asked him. 2 and 4 means that you don't count number 7 at all. Also, the only calculation, the order that you have to do it is
We'll figure it out. It'll all be great.
Yes. So again, the concept behind all of this is that if you've done the work and you've learned ROP and you've learned shell coding and you will learn and will have learned format strings and so on, you will do great. That's kind of the new philosophy that I've developed, where the starting philosophy was I wanted you to destroy each other. But it turns out there's not really that much from a, what's the term for teaching? The pedagogical perspective.
I mean, so will we still be proficient hackers by the end of this class?
You will still be proficient hackers.
Thank you. So we call ourselves hackers with like our LinkedIn account?
Yeah, I would. No, honestly, so on a personal level, like I've been super impressed. Office hours last week and chatter on the mailing list. I mean, you guys, some of you didn't know how to use Linux when this started. And you were talking about, hey, you have to do this and write a D word to the BSS and blah, 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 blah. And awesome. Awesome stuff. After my office hours, I walked into Fish's office and I bragged about this course. So I'm very proud of you all.
How does the administration feel about this course?
That we'll find out. My guess is no one really looks at drop rates and so forth until the course is over.
Right.
So, we'll see. Yes. We will see.
I mean, you warned us. You know what I mean?
I did warn you, and I think now I understand better on how to introduce these concepts more. First of all, I think doing a 2 class a week will help a lot. But how to introduce these concepts more gradually and less roughly.
Just out of curiosity, how many people solved the SROP challenge?
Let me tell you.
I did. Yeah.
The SROP challenge.
I'll calculate it.
You're counting?
I'll get it.
All right, Connor will get it. Okay, moving on. This is the grade distribution as of now, but this isn't the full grading implementation, right? So for sure that'll move to the right, hopefully significantly. But yeah, we have this inverse bell curve where half the class is getting an A+. Master hackers from homework 7. And I will read these names so that everyone is happy. Number 1 is plug and play. I think plug and play solved everything. Let's give plug and play a hand. You can de-anonymize yourself if you want. Give you 5, 4. All right. Good job, plug and play. Then we have elephant grass, who solved almost everything. Good job, elephant grass. And we have Dasher, who dashed past the curve and then kind of hung out. So let's give Dasher a hand. Dasher was the head of the pileup of 105% people, or 108, I guess. Yeah.
When I finished it, I only had like 40 points.
Yeah.
And then you multiply by 5, and I'm all right.
Yeah. Right. So again, the original plan was to have tons and tons of things, and we ended up getting all the ROP ones out there, but ROP turned out a lot more complex to grasp than I expected, and you did it, and that's awesome. But yeah. Okay, homework 7 strategy. So there was a route to automation, and we saw it fail in an in-class demo. If you remember a couple weeks ago, I went back that night and fixed that bug. But did anyone try ngrop in this homework? Did it work?
No.
Did it work for anybody? Okay, so this tells you something about the level of the tools. Did anyone do any other automation than ngrop? What did you do?
ROP gadget, ROP chain.
And it worked?
Yeah.
All right.
I don't think I submitted any of them because my submitter broke, and this is when I messaged you, and I just didn't bother to fix it.
Okay. Well, that's interesting. So ROP gadget has some.
It almost never works.
Yeah, that's been my experience, but I guess it worked this time.
I think I almost got Phone Tools.
Oh, the Phone Tools ROP
I
module.
almost got it. I was modifying the library Because it kept crashing it.
Awesome.
Python exceptions.
Awesome. Yeah, I've never ever used the Phone Tool drop stuff.
I scripted around RP++.
Oh, nice.
Just to find, because I had a common exploit.
Yeah.
And I just needed to find the gadgets to use
Yeah.
it. So I just grep through it and plug those into a little Phone Tool script.
Very cool. Cool. Yeah, so like a homespun sort of target-specific automation kind of. Who figured out the chmod shellcode? Who originated that? Both of you guys?
I sent that to you. Like, actually, I did that for the shellcode.
Yeah.
Assignment a long time ago. I told it to in office hours.
Okay.
And
Oh yeah, I forgot. Yeah, the shell. That's a really nice because that's a lot shorter, right? Specifically for this, it's very cool. In fact, I think you emailed me that after I pushed some of the later challenges that I expected you to have to pivot, but if you did chmod, you could avoid pivoting.
You can do it with just 3 keywords.
Chmod?
Yeah.
If you can pop 2 things, if you can pop RDI and RSI. Oh.
You would need 5 then.
Well,
You'd need 4 gadgets. Pop RDI, pop RSI, and jump to a
you can't
syscall.
get around
Oh, and REAC.
with
Yeah.
CHMod.
You have to get the syscall too.
Okay, so maybe.
Yeah, it didn't get me 9.
Okay, good. I feel happy about that. Okay,
Yeah, 9 was, I couldn't figure out 9. I spent a long time on
9 gave you 3 gadgets, right?
Yeah.
Yeah, 3 gadgets. 24 bytes. I could do it with 32.
Very cool. Who solved 9? How'd you get 9?
I called read from, so if you look at the assembly when it calls gread, it actually jumps to a function that does the call to, I think it's the GOT or PLT, I don't know. But it had, the point is that it calls read and then rets.
Uh-huh.
And so I would load 0 into RAX, and then RSI was already pointing to some string that was in heap space, but it was writable with read-writable memory. So I could call read again from standard in, dump a bunch of stuff there, and then return back and somehow move RSI into RSP. So I moved the stack pointer to the space that
Perfect.
I
Yes. Yes. So that's the key thing is that I wanted you to grasp is the stack pivoting that we discussed at some point in the chaos. Cool. Okay.
I was working on 9 before you made it position dependent.
Yes. Yes.
And I was like, fuck, man, this is.
Yes. I apologize about the initial 9 situation. I think Will, you told me that.
Yeah, I saw it and I was working on it. I was like,
Yeah.
there's no way I'm missing something.
I thought it was supposed to be like a return to libc kind of thing. Just go.
And where you override like part of their
That's what I thought initially because the leaked stack address, or the first thing on the stack should be something from libc.
Yeah.
Yeah.
I also was able to restart start and then have it leak some stuff off the stack and do it
And
that
keep
way.
running. And survive.
And run again.
Okay.
And read more data for you.
So you were probably almost there.
But then I said I have an A+.
Yeah. Yeah, that's interesting.
I think that's pretty much
Makes
every
sense.
challenge.
That's also a good strategy. Okay. So based on a lot of the emails I fielded and questions during office hours, I want to go through real quick and today talk about strategies to figure out what is going wrong when things are going wrong, and then we'll devote the rest of the time to format strings, and hopefully we'll be able to end a little early today because my throat is not 100%. I think I'm coming down with something, but we'll see. So, I beg you to start earlier. I had people emailing about how to set up RP++ yesterday. That's really bad news. So, it's starting early is important. I'm not telling you to start right away, in part because I've been falling a little behind too, so I typically push the first levels like either late tonight or early tomorrow morning, depending on your frame of reference. but don't start on the last day. A lot of this stuff, once you get the concepts, things go fairly fast. But getting those concepts is an undetermined amount of time. Likewise, when I was in college, I left everything to the last day, of course, did crazy all-nighters. But you can't email asking for an extension of a 2-week homework when I can see from the logs that you started that morning. You know what I'm saying? So, step 2, as usual, is panic, and that's okay. As always, panicking is okay. I tell everyone not to panic, but it happens. Based on, honestly, I expected a lot more of a drop-off right at the end because now we're past the withdraw deadline. But that means that you aren't panicking, that you're getting your panic under control. That's good. Step 3. The first thing when you sit down to exploit something is figure out what do you know. Right? And this boils down to, do you know where the stack is? Either on leaks or maybe SLR is off. This doesn't happen in our assignments, but it could happen, for example, if you're attacking an embedded target where frequently modern mitigations don't exist. Do you know where the heap is? Maybe you have a leak or some other situation is occurring. Do you know where the binary is located? So check if it's PIE. Do you know where, the other way around. Do you know where the libraries are located? Maybe you have a leak. Again, maybe SLR is off. Maybe you have a forking service, so it doesn't re-randomize. Basically, what control do you have what knowledge do you have that would allow you to write data to and read data from specific addresses that you can know, right? Of course, do you know the canary? In this homework, you didn't, but it was irrelevant. But sometimes you either know or can't find out the canary, right? And what do you need for the win condition? What is the knowledge that you need to recover? Specifically, the core thing of this homework was that in order to do code reuse, you need to know where the code that you want to reuse is. This isn't always necessary. Sometimes there are relative control flow transitions that you can leverage and so forth, as we saw with looping main. But you need to understand kind of what you know and how it can help you, right? And then you need to understand what you don't know and how you can recover it, right? So looping main to get it to leak, to get the binary to start back up and leak some additional information in these simple cases. In more complex cases, you often chain exploits to achieve a memory disclosure, and then you now know where some amount of memory is, and then you can start moving onwards from there. So, but the key thing is exploitation, especially in complex cases, is this continuous game of, moving up this mountain of knowledge and figuring out what is the next piece of knowledge that you need to obtain, and how can you do that? And then what does that new knowledge enable you to do? Once you know where the binary is, then you can start using a code reuse attacks and this sort of stuff. Then you implement something and it doesn't work, right? And this happens to everybody. It happens to me an insane amount of time, with insane frequency. Let me start debugging. So a surprising amount of people do not open up something in GDB and step and try to understand what is going on, right? This is an important thing. You can, again, something doesn't work, you launch it in GDB, You figure out when to break. We talked about different ways to avoid having to know when to break. So with shellcoding, injecting a trap instruction into your shellcode. With ROP, having your first gadget jump to a trap. But that's not even really necessary. You can reverse engineer the binary, figure out when it's jumping into your ROP gadget and break there. Or your ROP chain, and then break right at that return, in this case, from main. How many people use GDB single stepping in this assignment to debug shellcode? How many people wish they had?
I feel like it's a little bit harder though, like when you get to the pi challenges, because then you actually have to like attach to the process.
You don't necessarily have to attach to the process. So you can launch the process in GDB, and it just assigns it a constant base address, right? Like 555555555, whatever.
Oh yeah, that's true.
Yeah.
There are some really weird issues sometimes with launching the process in GDB. Like read sometimes just returns -1 and doesn't read.
Yeah,
That
I ran into.
that happens all the time.
But it doesn't seem to happen when you single step.
I had a lot of success with starting it in IPython using Pwn tools, and then just start
attaching.
GDB and attach.
Yeah.
You can do
So if you do
PS-AUX, and you can list all the processes out.
So yeah, if you
Find yours and
attach
attach it.
in GDB, it tends to work much better than if you actually run it.
My
in GDB.
GDB.attach is where it's using phone tools, uses GDB.attach process, and it would pop up the terminal with GDB in it.
Okay. I didn't separate
So, someone ran into issues with GDB.debug, right? Someone emailed.
I did.
Oh.
Did you ever solve it?
Yeah, I mean, it was, I think what I was trying to do was something that was orthogonal to what I was complaining about.
Okay.
Like what I was doing wrong was completely separate. It was, but I didn't really figure that out for a while.
Got it.
One of your challenges segfaulted my GDB every time.
Yeah, I kept segfaulting on the print chain instruction in GDB, but never outside of GDB.
In capstone with segfault?
No, I meant GDB
Yeah, I
itself
guess, yeah.
segfaulted. Yeah. One of his challenges caused my GDB to segfault every single time.
Yeah, it's this style of challenges where the challenge tries to walk you through how to solve itself is pretty tricky.
How does it segfault GDB though?
I don't know how it's segfault GDB. That's so one.
I remember. Yeah, I remember why it happened. Just it's weird.
Okay. Anyways, what did I bring this up for? Oh yeah, to show that we can. Whoa.
That occurred.
So if we let's grab a PIE one.
What was your intention with Baby Rock 9? One thing I was trying was to pass a ROP chain through RFB. Of course, that's not going to work if you have null bytes in it, right?
Yes.
And then I tried an environment variable, which you can also not store null bytes in, right? Just to put some data on the stack.
You can't
Null bytes
store.
are terminated. I mean, environment variables are null terminated.
Exactly. So if you have any null bytes, which is common in ROP,
So you can store one null byte.
Well, you can also store multiple environment variables.
Yeah.
So the environment variables also, the name is stored.
Yeah.
Just quite useful.
And you can control the order in which they're put on the stack.
are they because they're ordered or?
Yeah. Like the order that you pass into exec-v.
Is that what you intended?
Yeah. So what I wanted you to do.
Can you demonstrate that? We have time.
Let's try it. So.
We can do it later on.
Okay. Yeah. Let's do it after the thing. What's up?
I just wanted to check, are we recording?
Yes.
With voice.
We are recording, and I think we have voice, but it's. I did a demo one, but without stopping it, it's hard to tell. Okay. Yes. So. Baby Rock 9. Oh, right. So I opened this to.
Is Chowder the name of your challenge generator?
It was. I needed a Pwn chop.
That's a better name.
Yeah, I agree. All right, so
Lone Star would be pretty good.
Lone Star.
That's the solver.
Exactly. Okay, so
Where do you keep them? Is there a repository on Hub?
So when we start up PIE executables, GDB puts it at this 5.555.
You're right. I definitely was not thinking about that.
Yeah.
But like towards the end, like 6, 7, and 8, but if you got your raw chain for 5, you knew exactly what to do. So like you didn't even need GDB at that point. Like.
Yes. Yes, exactly. You just needed to know how to rebase it.
Right.
Yeah. So one is this concept. The other thing is when you're ready to take it outside of GDB and you don't want to deal maybe for debugging on a core file, as we'll mention in a second, don't forget this ability. This command launches a bash with ASLR disabled. So from here, we can, whoa.
That's not going to work in your Docker container.
Yes, maybe not in my Docker container, but you can debug outside of the Docker container and then bring that in. ASLR equals false, yeah, when you launch it with Clone Tools. But I doubt that'll work in the Docker container either. Probably does exactly this. So when we run here, when we run here, we can now attach to it. Actually, and then god damn it. Do you remember the command that you have to echo 1, 2? Yes, this one. No, whatever. All right. You can do info proc map, and you can see that this ended up disabling SLR as well. Now you can deal with debugging it without ASLR, as long as you keep in mind that when you're exploiting it, you should properly leak addresses and so forth. But in this case, you have the known base address and the known library addresses as well. So that's an important part of debugging this. Then, who used GDB scripting in this assignment? Nobody. I guess it wasn't super crazy necessary. I think with GDB scripting, you could dump a lot of interesting data as you single step through your shell, your ROP chain, but GDB scripting is very useful in general, and you should all learn it. So, let's say GDB, aside from GDB, what can you do to debug your payload? You should, I have strace there twice, because you should always strace a payload that almost works, but not quite. Right? So a lot of the exec-VE issues that people were having could be very easily debugged with an strace to see what exec-VE was being called with. And while we're at it, if you're trying to pull off something complex and it's not quite working, especially if it's a ROP chain and you don't want to step through it in GDB, copy-paste the assembly instructions that the ROP chain represents minus the rets. Instead of the rets, just do a subtract RSP or an add RSP, and paste it together into shellcode that you can then either single step or strace in GDB, or single step in GDB or strace. Does that make sense? So a lot of the issues that I was seeing people having with trying to put together exec-v call sites and so forth could have been very straightforwardly debugged with this method. Just figure out, oh, okay, that's what's happening. This is what the kind of memory layout is at the exact point where I call syscall, and these are the gadgets that I need to insert or change to make it correct. Another thing that's very useful is, you know how when, like with a, supposedly with an artillery installation, you have tracer bullets that fire every some amount of bullets that light up. You can do the same thing with gadgets. Whether you're writing shellcode or you are doing some crazy ROP stuff, you can have either tracer instructions, which just sit there and loop forever, and you know at least that the program made it there, and maybe you can even attach with GDB and debug. Or you can do the same thing in a ROP gadget. Return to an instruction that causes the program to freeze, or that causes the program to try to read data and hang and wait for a read, and then attach to it and figure it out. And then, of course, again, strace is your friend. Use strace. It's very useful. Okay? Cool. Finally, strace is, if all of those fail and you just have no idea what's going on and your payload is crashing, consider enabling core dumps and then opening that in GDB. It helps you look at the exact process state when the process crashed without actually having to single step all the way up until you trigger the crash. Okay? Did anyone use core files in this assignment? See, this dude did. He's super lead. Cool. So just keep in mind, you have to enable core dumps. Cores are off by default nowadays. Back when I started using Linux in 2001, core dumps were on by default. Whenever a process would crash, it would save its entire memory state on your disk. And this was hell because all of a sudden you'd find out that you have no memory left, or you have no hard drive left, hard drive space, and it's because it's full of cores. But things are not like that now, unfortunately, because back then, anytime you had a seg fault, you had a nice core laying around. But now you can enable it and debug. Cool. Any questions about debugging, shellcode, ROP chains, how to adapt when things aren't going well? Brilliant. Any suggestions from the top people that I missed?
Yeah, I mean, I just did what we did in class, where you just restart the thing and you get leaked everything, and that solved everything up through 9. Up to 9.
I did that also.
Nice.
All of them.
Nice. Through 9, so you solved 9.
No, I did not get 9. Not, I mean, because 9 you can, like, you're limited in space, so I knew everything. I couldn't.
Yeah. But you managed to, you rewrote like 2 bytes, and that would restart things.
You can write 1 byte, because you just go back to libc and then you just go up a few lines.
Yeah. Cool. And that's what you did?
I don't remember. That was a while ago. Yeah.
See?
Wasn't sleeping.
Zach started early.
Oh, I just did it when you said that there were new challenges available, because I knew I'd be busy afterwards.
Nice.
And I was very sleepy.
All right. Cool. So, Connor, anything that people went to you in the office hours?
I think you covered everything.
Only 2 people.
Only 2 people came to office hours?
No, for his SROP.
Oh, for his SRAP.
Solved. We don't know how many people it's happened.
Who tried, like, did a serious look at the SRAP? right, 3 people, 2 people solved it.
67%.
All right. You can talk to Zach. That was his guest challenge. I disabled that challenge for him, of course, but it seemed like a good challenge. All right, format string vulnerabilities. Everyone's tired of this, but let's push through them. We'll give it an hour if we go home early, or probably we'll give it 3 hours, and you'll all really hate printf vulnerabilities by then. All right. As a reminder, format string vulnerabilities happen when a format that is user controlled is passed to printf directly, or a number of other string formatting functions, such as sprintf, snprintf, fprintf, fnprintf, all sorts of fun printfs. So there's also interesting things with scanf, all sorts of great stuff. We covered that printf works. It is vulnerable because printf has to retrieve the number of arguments that it expects from the format string. If the user controls the format string, the attacker controls the format string. The attacker can control exactly how many arguments printf reads in. We talked about how printf grabs locations grabs arguments from registers and then eventually starts grabbing them off of the stack. And that's super interesting because you can use that to leak memory using %C for single character, %X for a D word, %S for a string that's dereferenced from a pointer on the stack or in the register. And you can control how much you leak. So you can do %LX to get all 64 bits, %X for 4 bytes, HX for 2, HHX for 1. You can directly reference specific arguments using this nice syntax that, for some reason, the glibc developers have provided us. This is a problem not just when programs are super lazy and just give you a printf of your input, but happen for non-obvious reasons when a format string is dynamically generated and passed in. And we had that example of a format string that centers your what you're trying to print. As a quick aside, there was an entire year of DEF CON CTF, the World Championship of Hacking, where every single vulnerability was a format string vulnerability. That was not very well received by the community, but it happened. So take that as what you will. Maybe that says that it's important, maybe not. What's up?
Was OO editor also a format string vulnerability?
No, it wasn't this year.
Oh.
God, no.
Yeah.
No. It was 2012, I think.
Oh. Okay.
Yeah. It was, like I said, it was not well received by the community. But format strings vulnerabilities are super powerful primitives because not only can you leak memory, but you can also write memory. So the idea was that this could be used for alignment in a format string and blah, 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 but it's only ever really used by attackers. This functionality is likely going away, likely in the not far future, but for now it's still with us. We can still write memory using %that. And we went over, of course, why this is bad. And we got into this super confusing example where we could overwrite certain return addresses, saved frame pointers, on the stack because we had other frame pointers that would point to them, right? This is relevant because %n, to write memory, it requires a address passed in as an argument. So you could use one of these frame pointers as the argument, this one right here, and then you could write over the value that it points to.
Couldn't you also overwrite the last 1 to 2 bytes of the return address just to loop back to the printf? So the first printf would be to leak something, but also overwrite the return address, and then
Yes.
loop back, and you'd be able to keep doing that until you.
Yes, exactly. So we'll cover these sort of things a little bit today. So this is a very fancy thing, and honestly, it was the wrong thing to charge, the wrong direction to charge down, because things are actually much easier. I kind of skimmed over this. I said, oh, if our buffer is on the stack, then you can just use values inside our buffer as the pointer that will be referenced to do the write. Right? So I want to go back to this and show you how that'll work. The scenario, these printf vulnerabilities don't just happen in a vacuum. You don't just, inject your format string and then printf happens and that's it. When you write your format string frequently, not always of course, but sometimes is on the stack. And this is the simple case of a format string vulnerability. So if you remember when I had my example, this is class 9, right? No. Is this class 10?
Are we counting the classes we didn't have?
Huh? So we have this print.c from last week. And this print.c had main calling foo, bar calling, main calling foo calling bar, and bar calling printf. Right? And it printf our argument, and then it did printf a new line. And if we compile it, actually, I want to show you something here. Okay, never mind. All right, so if we run print, and then we give print ASDF, that's great. Print %lx. This isn't a surprise to anyone, right? So we can, by using %blob, by using these format string arguments, we can leak memory, and we can write memory, and then we can also eventually overwrite something that's not a pointer. Oh, wait.
Space. Yeah.
Thank you. And then segfault. Cool. In this example, our format string was on the stack, right? So when we called printf, at some distant offset, we could find our format string. So let's give that a try. Let's find our format string. First in GDB. So we'll break at printf. Say our format string is just a bunch of A's. Hold on. As embarrassing as this is, I gotta Google to remember how to disable this.
Child.
Huh?
I can't remember off the top of my head. You can tab to it. Set child. Forking.
Set follow fork.
Yeah.
No, it's not that. It's the hold on. It's the mitigation for that one vulnerability.
The ptrace?
Yeah.
Oh.
I just don't remember the file in /proc or /sys that I need to write. Oh, yeah. I had the file right, but not the argument to it. So you need to write 0. I wrote 2.
For what?
That's so backwards.
This file. there was a big vulnerability related to the ability to attach to processes that that are sensitive as a user, and now by default you need to have well, by default doesn't work, and sometimes you have to enable that option in the kernel. It's not a big deal. We did it. Now we can run. Okay.
Is that an 1804 thing?
Yes.
And that's even if it's your users that's running
Yes.
the process, you still have to have this permission.
You shouldn't need it if it's your direct child. So
Right.
I'm a little confused about why that was happening.
Yeah.
But maybe it's some Pwn debug stuff. Honestly, we're not going to go down that rabbit hole. We could, of course. So we break at printf. We run with our injected format string, and now we're in printf. So the question is, where is the format string? Printf takes arguments. How's the first argument passed? RDI. So let's see. Access RDI. There's our format string. A repeats a bunch of times. And we can see RDI is here. Points RDI has this value. So our format string, if you look at the VM mapping, is here, which is the stack. So our format string is on the stack. This makes sense. Why is it on the stack? Because it's argv1. Args are on the stack. So then if you look at the stack, there's quite a lot of stuff on the stack. If you look on the stack, we have our format string. What's the stuff below the format string? What's this stuff on the stack? Environment variables. So you can see that's part of some environment variable. That's part of some environment variable. Yeah, that's part of some environment variable. So our environment variables are on the stack, and we can use %x to eventually leak stuff off the stack, right? And %n to eventually overwrite stuff by dereferencing values on the stack. So what we can do, let's leave GDB behind. We can find our value on the stack. So do lx. That's obviously not our format string. Format string. Actually, let's add some a's.
Should be second argument, right? Pass through a register.
The format string? No, the format string is the first argument. If you hit %, oh, what do you mean?
What's the second argument pass through?
Oh, RSI.
RSI.
Yeah. So, yeah. Okay. So if you hit %x, so this is the value of RSI at the runtime, at the invocation of printx. Does everyone understand why? No. Okay, let's do it in GDB. So I'm doing %lx.
What about your A's?
Fuck days. So we have %lx, and if I hit continue, it prints this guy, right? This is because printf has been run with the following: %lx and nothing else after that, right? Nothing here. Because if you look at the source code, it's just printf and it passes one argument. So when the compiler compiles this, oh god. Did anyone take Adam's class? Adam Dupé?
Which one?
Any class where he taught like assembly?
545.
I think he does AT&T.
Yeah, that's. I found this out like last week. He really does AT&T.
I think so.
He just does whatever's default, and he reads the correct one.
He shows you that Intel exists.
That's insane.
Well, he
But if
says
you know
can
Intel
tell,
exists,
but you can tell based on-
why would you use AT&T?
Because he just does the default one, and he just looks to see where the literal is to know which one it is.
That's what his strategy is.
Even in his exams, you can see that.
Oh my God! All right. Anyways, it's fine. Adam is best teacher in CSE several times in a row. So, what can I say?
That just seems emotionally devastating.
It is. Yeah. You see that. All right. Anyways, back to reality. So, we had print of argv1. How did that get compiled? That got compiled into eventually a call print, of course. Move 0 into EAX. Whatever. So RDI is the first argument. It comes from RAX. That comes from reading, dereferencing, blah, blah, blah. I mean, it comes from somewhere, but it's basically argv1. But you'll notice over here, nowhere does it set RSI. And that's the second argument. And that makes sense because we only passed one argument to printf. But now printf is expecting a second argument. Right? So it says, ooh, %x. That means that I was passed in an integer to print.
Oh, that's RSI.
And that's RSI. And so if we now look at exactly. If we look at RSI, that's RSI, right when printf starts. And if we continue, that's what got printed out. And if we put %x, or LX, of course, %LX. So RSI is going to be the first one. What's argument 3? RDX. And what's number 4? RCX. And number 5? R9. Yeah, I honestly don't remember. So if we hit continue, here's RDX. And here's RCX. All right. So let's actually do a bunch more. Okay. So what is this? Will be the first argument, second argument, third argument. What's the fourth argument? R9.
R9.
R9. And what's the fifth?
10, and then I think 11.
I think 315.
No. The others are on the stack.
Everything else is on the stack. And of course, first we have the return address here at RSP. So we start at +8, +16, +24. So if we hit now continue, here's what we're printing. This is RSI, RDX, RCX, R9, R9 again.
This was happening in the last class.
I think it's R11 next, actually. It's really
RDI, RSI, RDX, CX, then 8, then 9.
Then 8, then 9. Okay. Cool. So let's do that. Now let's actually have a couple. Okay. So RSI, RDX, RCX, R8, R9, and then what? Everything else on the stack?
Yeah.
Perfect. RSP plus 8, 16, 24, 32. Continue. All right. So here we have our 8, our 9. Whoops. Then we have this guy on the stack, and then we start reading from the stack. Stack.
That's the RC.
And the stack. So these are.
9 in the stack.
I'm sorry.
What's the 9 in the stack? Is that the %sign LX or what is that?
The 9.
It's the number of the arguments we passed.
Number of arguments passed.
I guess.
It should not be the number of arguments passed. That doesn't make sense.
Is that?
Well,
Yeah, because that's not the number of arguments
just
passed. We passed one argument.
Yes,
Because
exactly.
we're reading the stack of the function.
Well, we're only passing ls, ls, ls
Yeah.
in its own
Let's find out.
That's one argument.
So, let's break main. We'll run with the same thing. So we'll go, actually we'll step into foo. So let's look at RSP here has no 9, what to speak of, right? Let's keep stepping. Stepping. Stepping, stepping, stepping. We call bar. Still no 9. Okay, here, oh, okay. It was just uninitialized space on the stack. So the 9 appeared when we allocated stack space for the function. It just happened to be there.
Is that like the argument? Is that like maybe the first argument is expecting or something? Or what is that?
Like, what is the 9 specifically?
Yeah, is that like gonna play it back every, I guess, some like some challenges?
So the 9 is what happens to be at that value from a previous invocation of some other function that freed its stack frame. But of course, when you free the stack frame, you just shift the stack pointer. You don't overwrite the data. And then when bar ran and bar made space on its stack, suddenly the 9 just happened to be there, right? So it has no bearing to bar or to printf. It has bearing. It was used at some point in libc when libc was initializing stuff, right? It wrote that to the stack, freed that stack frame, and then we just happened to allocate over it again, right? So the question, does that have any bearing when solving challenges? Of course, is yes. That's information that you might be able to leak because that data wasn't cleared, and maybe the program even naturally just prints it out to you, right?
If you were to run it again, stop everything and run it again, it would be different.
It was the same.
It's likely going to be pretty stable. Like if it's an address, it'll be whatever, all properly aligned. But it's some value that libc specifically wrote. We can actually, if we want to do this to ourselves, we can try to set a watch point.
Will it help us understand format strings better?
Probably not. Let's just see. All right. So we created a hardware watch point. Bear with me. We're going to rerun this. Boom. We've found what wrote to R9, and that is some initializer code in the dynamic loader in Linux, in libc. So this is, as you can see, starting up the process, doing something, and then of course this is going to, we're going to hit a bunch of these. This also touches that part of memory. Yep, this touches that memory, and then we're in main. So it's only touched, that part of the stack is only touched during initialization because it starts running, functions start calling each other, it gets to that deep into the stack, writes a 9 to it for whatever reason, and that's beyond out of scope because who knows why. And then when it frees it, when we eventually get back to that stack, it's still a 9. Does that make sense? Cool. Okay, so let's disable that breakpoint.
We take a break.
Let me finish making this point, and then we'll take a break. So we'll find our format string. We'll take a break. Is that clock an hour? Oh.
7:30.
It's 7:22.
Screw that clock. Okay. Cool. All right. So we're at printf. Okay, so anyways, we determined that here is where, from this 9 is where we start leaking our stack. If you remember from last time, we don't need all of this crazy stuff. We can say percent, and this will be 1, 2, 3, 4, 5, 6 to target the 9 directly. What?
That's not right.
Oh, sorry. Yeah, I had that one the wrong side. Yep, here's the 9 directly. Cool. And now, let's disable the other breakpoints. And now we can start, actually let's get out of GB. So we have 6LX, boom. Why is that different?
You need the dollars.
Thank you.
Make sure
Cool.
to it.
So now we can do something like percent 100LX. And now that's some pointer on the stack, probably something on the stack. This keeps changing, that's annoying, so let's set arch x86 64-r. Boom, yep, now we can see that that's a stack pointer. Let's keep going in the stack. All right, that's a pointer to the binary. Now we see some stuff. What does this look like to you?
Environment text.
Yeah, that's
Why does it look like text?
39
Yeah. Eventually, you have a sense, right? So now we can. Let's actually split the screen here a little bit. Why? What's going on? There. Okay. So here it is. We'll grab IPython, and we'll have this guy. Some text. So if you remember from when we were running it in GDB, actually GDB, one thing that I'll mention that I painfully learned recently in the course of some very painful research is that GDB rearranges stack variables when it launches the program. So we're talking about
environment variables.
That's what I mean, the environment variables. It rearranges them.
Yeah, there are 2 environment variables, column and.
It adds 2, yes, in GDB, but in GDB server it won't add it, by the way. So that helps. Or you can just set them and then the stack just shifts.
Yeah.
But it rearranges them. That's insane. It's insane to me. So when you're trying to synchronize, anyways, it's insane. It should not be doing that.
Never start a program with GDB. Always attach.
Yeah. So if we start walking back on our stack to find, oh, actually, let's add some A's here that we can find. Boom! Wow, got it in 1. So 156. And then we print out our A's. Cool, huh? Yeah. So now, let's pretend that we wanted to write to it. We do %n, and of course it'll segfault. But it'll segfault. Let's ulimit.
What's that ln do?
A %ln will dereference the value that argument number 156, as a pointer and write the amount of bytes that we have written thus far. It's used for alignment. It's a stupid idea that made its way into libc, and now we also have to suffer and or have fun, depending on your point of view for it. So we did this, core dump, GDB print core. Here we are at the point of the crash. Let's do that. Okay, so the point of the crash was moving something to RAX. And if we PX RAX, it's our 414141. Cool, huh? So, we found our format string in memory. Let's take a break. Actually, let me pause the recording so you don't have to fast forward to it. Okay, so we have now demonstrated that your format string is on the stack It's not a lie. Now let's figure out how to figure out. I mean, how do you figure out what part of your format string is being printed? So we've got this thing going on. Oh, sorry, hold on. I was demonstrating something. All right. We got this thing going on. We put a bunch of A's. And then here's the actual string.
Home tool cyclic.
Yeah. So we can figure out where in the format string this is by using cyclic. Who here remembers the cyclic stuff? All right. So if we pull up IPython, pwn.cyclic dot, wait, I forgot. Yes. So cyclic 100. Here's a cyclic string. So we replace our A's with that cyclic string. And you can see, why is this a null byte? I guess because we were at the very end of it. No, that doesn't make sense. All right, let's increase the size of this cyclic string. Okay, so here's a cyclic string. We decode hex.
First 4. Cyclic only takes 4.
I'm sorry?
Cyclic only takes 4 bytes. It'll whine at you if you put in all 8.
Oh, cool. So I just put this, right? CAA? No.
Cyclic underscore find.
Underscore find. CAA. And we are 8 bytes into our format string, which you can also, of course, confirm by yourself manually the hard way. Here's AAA, BAA, CAA. Nice and easy. So then, if you're 4 bytes in, then if we look at argument number 155 instead of 156, and we decode this as hex, hold on. Oh, okay, so this was CAA and BAAA was argument number 156, right? And why is this? Oh, interesting. So, why is C before B over there?
Little endian.
Little endian, exactly. Something I embarrassingly forgot. And so if we actually byte reverse this, whoa, wrong way. Byte reverse it after decoding it. Look at the individual bytes. It's AAA, AAC. So that's very different than CAA, BAA. If we do cyclic dot find, cyclic find of this, it's position number 1. So that's it. So this is 1 byte into our format string. So if we do 55, let's decode that. This is argv0, the end of it, and the null termination. And here's the beginning of our string, right? But we basically found this through trial and error. So this is kind of the first 8 bytes that we can directly control on the stack. We found it. How? By setting it to a high value, saying, okay, this is weird things in the environment, whereas argv should be a lot earlier, and basically playing with it until we find argv. This is the stupid way to do it, but it's very effective eventually. The correct way, we run it in GDB and we do what we did the first time. We dump the entire stack. We see where is our format string, and then we do the math. We actually how many 64-bit words are there between the stack pointer and where we actually want to print. We should probably go through that in GDB, shouldn't we? So let's figure that out. Here we run GDB. Let's say one word of caution is that changing the size of your format string changes the stack layout. Changing the size of your arguments to the binary changes the stack layout. Why is that?
Because it's on the stack.
Because it's on the stack. Exactly. So if you pass in a 1-byte argv, then it has 1 byte and a null byte. If you pass in like a 300-byte argv1, it'll have 300 bytes. Stack offsets will change. My big suggestion to you is to keep it constant. Pad it at the end if necessary. So when you are running a program that takes a argv format string or whatever, or an environment format string, keep it the same size. Pad it at the end after you're done.
Unless you're dereferencing your own format string, right? Then allocation also should be fine. Right?
What?
Unless you're dereferencing your own format string, then it shouldn't matter what the length of your format string is. Because allocation would be called.
Yeah, well, yes. So, I mean, anytime that you need to know offsets on the stack, right? Or offsets if your format string is allocated with malloc on the heap, offsets on the heap.
Yeah.
Anytime that those are important, you want to maintain a similarly sized format string. So, let's do this. We'll do here it's easier not to use the cyclic, and then we do %lx, and then we have everything afterwards. And we're just not going to change the size of this format string. So we print this. Let's break at printf. We run it.
Nice.
px rsp. This is where the stack pointer is. So it's going to start reading arguments at here. That should be our 9. Or not. I mean, for whatever reason, it's not 9. So let's actually run %lx, 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 %lx. There is a 9. Oh, interesting. So this is an interesting thing. I wonder if... So, I just ran this format string, this big monstrosity, right? And all of a sudden, if I look at RSP plus 8 on the stack, oh, it is a 9. Did I just not see it? It was 0 before.
Oh, because.
All right. Anyways, so if you run this, and our format string is AAA, and then the format string and a bunch of B's, right? And the question is, how do we compute what this has to be, this offset here for the argument number? We can... This is going to be the first thing we get off the stack, the first argument number, and that is already argument number 5, 6. Our RDI is the format string. Our SI, our DX, our CX, our 8, our 9. So argument that's 1 through 5, argument 6 gets off the stack. So just as a sanity check, if I change this from 1 to 6, continue, here's our 9, brilliant. So, this is where it starts if we do our print out the entire stack. Scroll up far enough, we can see our A's. So here is where our A's start. We have 2 bytes in here, and then we have our A's, our first fully controlled 64-bit word at, it looks like, FFFE100. And if you look, and if you subtract RSP from that, and now we have to get some really annoying stuff. We have to cast RSP to an integer type. Let's actually, fuck. Okay. That's how many bytes are between them. This is how many words are between them. And plus 6 is how many, so it's 155 words on the stack, and then on top of that we have 5 or, would it be plus 5? Plus 6. It'll be plus 6. 6 is when we start counting at, because of all of the argument, the registers, the arguments in registers, and that's 161. Sorry. And then here, I'd mute my, oh, hold on, did we unpause recording? Yes. I'd mute my audio, but I'm afraid that'll fuck up the recording. So, all right. So here we put in 161, continue, and here we have our A's. And this should be these A's here.
So change the first one.
Let's say haha yeah, continue, and here is our A. Yeah, so let's decode that. Oh, what?
Yeah.
Aha, yeah. Okay, I was up by 1. Oh, that's right. Sorry. If you look on the, when we leave the stack and did this calculation, there are 2 A's, and this starts from the 3rd byte.
I thought that's why you did the plus 6.
No, that so we'll go back over to plus 6 in a second. All right, so we did this,
H,
and here is H A H A Y E A H. Cool. So why did we do the plus 6, Robert?
Because the first 6 parameters are in registers.
First 6 parameters, well, first 5 parameters in registers, and then that function was 0 indexed, and then we did plus 1 more, because the registers are 1 indexed, for whatever reason. Exactly, because of the registers. Does that make sense to everyone? Cool. So now, you have 2 methods with which you can find the format string. Which one should you use? Honestly, the sorry, the hackier one is probably easier, especially because you control, when you control the environment, and in these challenges you do, or the arguments, and in these challenges you do, you can push gigantic arguments and basically increase the chances of a random guess hitting somewhere in your arguments to very high levels. So if we, for example, are really lazy and we don't care about elegance necessarily, we do a cyclic of a ton. That's a lot. That's a lot. All right, so this, okay, that's even too much, but okay. Let's say 2048. That's a big cyclic. We can run it. And it's also easier to have the cyclic after. So we say, okay, this is going to be space for our format string, our amazing format string.
Why don't you just do the dot, the put 10 characters thing, the star?
I want my format string not to change size when I play around with it. And then we do percent, I don't know, 200 LX. And you can see that wasn't it. percent 300 LX. Seriously, that's still not it? Percent. Oh,
Oh, you're doing percent.
I'm not doing the dollar sign. Okay, so here we have, this is a bunch of lowercase numbers or letters that decode hex. Yeah, and then we do cyclic dot
Underscore
tone dot cyclic find. Boom.
Only the first 4.
Only the first 4. And it's 993.
I'm unsure, but cyclic find also might accept it as a number.
Oh.
I'm unsure of that though.
Let's try it. So we have this one. No.
Again,
Well,
it
but
would
that's,
Oh.
yeah. That's not.
Whew! It does.
Nice.
That's cool.
That is cool. Alright, here. You take that. The first 4, 6.
Do you have to unlittle and delete?
No.
No,
Oh.
it takes it as the one.
Yeah.
Because that's your architecture.
That's cool. Okay, I'm impressed. Anyways, but you see, by spewing a ton of data in here, I made it much easier to figure out where my format string is, because there's just a higher chance of me guessing a random number that happened to fit in it. And then I can do stuff like, okay, so then what can we do from here, right? We have a format string that we know that is injectable, and we know where our format string is in terms of the argument number here, right? Of course, as we saw before the break, I can change this to %n, and things will crash, right? But that's not super exciting because things will just crash. What else can we do? So let's actually start a Pwn Tools thing so we can do this automatically. And let's work without ASLR for now, and then we'll generalize this, or maybe you'll generalize this. So import pwn dot process print ASLR equals false, and then actually. So here's our format. If we look at, okay, so then what's our format string going to be? Our format string is going to be %300 $LX. We will left justify it to, I don't know, 128 bytes, and then add pwn.cyclic. And what did I do? 2048?
Yeah.
All right. So this should output r.read line dot split. This is our leak, and let's make sure that it makes sense. That's 0. Okay, this looks like some cool stuff. And now we can do.
Instead of doing LX, could we do, what is that, HX? And that way I don't
Yes,
do the 4.
I can do HX. Pwn.cyclic find leak, and it's -1.
You have to.
Yeah, you have to convert that to an integer.
Yeah.
Just
Thank you. Sorry.
I didn't delimited it, right?
I'm sorry?
Shouldn't you limit it to?
Couldn't you
4
just do?
characters?
Oh, I did HX up here instead of.
Oh, okay.
Sorry, not HX, %X. That would be.
Yeah.
And here it is. So it's a little different because GDB had, or in Pwn Tools, probably the stack is slightly different than here, but it's 969. So now format offset is this. So now we will see what happens if we do a write. So have our evil format is %. So this gets kind of screwy if you're building format strings using format strings in Python, but we'll bear with it. So we had %, and then we will have our 300 n. Actually, it's not going to get screwed. Justify 128 plus 969 bytes of the format string plus the address that we want to write to. And let's do 1237, 1238. And then we'll justify it this all to 2048 because that was the size of this format string. And we want, or the size of that part, the cyclic part of the format string, the size of our payload part is 128, and we want to keep all offsets the same. Oops. So now we have our evil format, and now let's run this with our evil format. And let's make sure it crashes. Yep, it crashed.
Well, you didn't set it to evil format yet.
Yes.
Thank you. It didn't crash, it just quit. Okay. Huh? Not enough parameters. What? What? Inappropriate nulls in RGB.
I think you have to escape the percent.
That should work because you're not formatting.
I'm not formatting it. Hold on,
Where's your nulls?
I have nulls, of course I have nulls. This makes sense because I'm trying to encode an address in here.
Yes.
Okay, here's the solution. And it's a nice, easy solution. We change this.
Read into the file.
Yeah, let's just have foo var, and then it'll just say,
Just
hey.
change the target program.
Huh?
Just change it.
Just change the program.
Can we do this during your challenges too?
Exactly. We'll get to the hard case that we were looking at just now, but first let's get the easy case. So let's do our format is a, I don't know, 4096 thing, and we will simply read 0 format 4096, and now we'll just print that format. Nice and easy. I highly recommend making your challenges easier before you do them. So print.c actual print, a few arguments to some function. Brilliant. So now print runs, and now beautiful. Okay. The likely situation now is this no longer works. 300 might not seek into the middle of our format string anymore, but it might. So let's see. Oh, right. So now we're no longer. So let's do this. We'll create a helper function to try our format f, and the format will be f.ljust blah, and then we'll put, never mind. It'll start this up, and then we'll do r.send f, and then return r. Okay, so we have this format, r equals try format. Now this should leak again, and let's comment this out now. Offset is -1, so we guessed incorrect. It got something, so let's, maybe it's not 300, but let's try 200. Aha! Great. We'll do something smaller. 10. Nope, not good. Alright. We shouldn't have stared the gift horse in the mouth. There we go. Offset is 626. We'll be happy with that. So now we build our evil format. We have our 100% n. I'll adjust this. And then here is now the leak, of course, or the format offset. Sorry. Format offset. And then we send in our address. Justify that. And then we will try format of the evil format. I have that interactive. Okay, so that should have crashed. No, but it did not. It exited.
No, it says I got a 6.
Wait, where?
6. Yeah.
Oh, yay! Okay, it crashed. Beautiful. So it crashed. Hold on. Let's ulimit -c unlimited so that it actually runs.
What is the
I'm sorry?
What does that do again?
So ulimit is various limits for your process context. -c is the size of a core file that the kernel will write when you crash. There's other interesting stuff here. -n is the number of files, or rather, the value of the highest file descriptor that you can open.
Yeah, I've had to do that for AFL.
Yeah, for AFL, most of the time, the biggest use of this I've seen is Java or other. There's an interesting situation when you have a garbage collecting language with a garbage collector that is not non-trivial. For example, if you do this in Python, so this will print out root, right? The first user at CPassWD. And I can do a while loop indefinitely in CPython. Fuck. While true is the F. And it'll keep going for a long time and never crash. Because in Python, this is a complete tangent, I apologize. In Python, variables are freed immediately upon going out of scope. When there's nothing else referencing them, they're freed. And when the scope of the function is exited, there's nothing else pointing to the local variables unless you store them somewhere. They're all freed. So the file object returned by this is freed. The file descriptor is closed. If you're in a PyPy Python, and this is Python 3, so I have to change something. So this is PyPy. It's a Python interpreter with a much more advanced everything, but also a much more complicated garbage collection module. If I do this, it doesn't garbage collect immediately. Files objects stay around until it deems it correct to free them, and we start hitting these problems. Anyways, so you saw how fast we hit it. If we ulimit You can't ulimit -n unlimited, unfortunately, because every file needs a file descriptor, and this takes up resources in the kernel, and obviously you can't do that. And I think normal users can only go up to 4,000 at least. Yeah, I guess 4092 is my guess. Oh wait, well yes, now that I've said it, I can't change it. Anyways, so now it's 4,000, and you'll notice that it's going to.
Oh, you can only go down.
Yeah.
Limited.
Yeah. So you can survive for a little bit longer. Anyways, tangent over. Who found that cool? All right, there you go. Cool. All right, so back to the evil format string. Why did we even go on to that? Oh, yeah, ulimit. So that's what ulimit dash.
You got to unlimit the core.
Yeah. So.
Your core file is going to contain the whole address space, everything that's loaded in memory.
Yes, exactly. Yeah. Yeah, I don't know. What's the point of? I mean, why would you ever have a non-unlimited? I guess just to make sure that it's just not filling up all your hard drive space. All right, so we ran it. It dumped the core. If you look at what's going on in the core, it's writing to RAX. If you look at what RAX is, 1337, 1338. So we're trying to write something to 1237, 1338. Pretty cool, huh?
Is that printf positional exported in libc, in the trace?
The printf positional? Like can you call it directly?
Yeah.
I don't know. Let's find out.
That null byte problem. How do we get around that?
We will.
Did we?
We did not. Oh, we did a read instead of argv. But we'll get around it. With this, it might be. We'll get around to it in a second. All right. So, gc-test.c-o test. No, it is not. Cool. Okay. So, the basic end result is that we were able to kind of automatically-ish determine the offset into our format string, and then dump a pointer in there that %n would use to dereference and write to. So that's pretty cool. We can also use %s to read from it. This will also crash because 1337, 1338 is not mapped memory, so here it crashed. avgdb that core again. You can see here it's doing some crazy stuff. Who can remind me what this instruction does? It's a vectored read of size. Yeah, of size. So basically, it's a hyper optimized version of strlen to try to figure out where the null byte is in the string.
It's a compare equal what?
It's vectorized, maybe pointer compare to equivalent byte is my guess.
AVX.
Yes, these are like this is where x86 gets really crazy.
How many bytes is this?
Oh, is this instruction?
Yeah.
5. It's 4 bytes long, surprisingly.
It acts on a lot of data at once.
Yeah, it acts on a lot of data at once. Anyways,
I've never used those registers actually.
I'm sorry?
So I've never used those registers.
Those registers are fun to use. Anyways, the point is, what's RDI? Is 1337 1320. Why is it not 1337 1338? This is kind of an aside and not very important. Matt said, so I bet he knows. So these crazy instructions require alignment. They're very fast in the sense that they can act on tons of data at once. These YMM registers can act on 256 bits of data, but they have to access 265-bit or maybe 128-bit aligned. Well, this is just 16-bit aligned, right?
Yeah.
Anyways,
16 byte aligned.
yeah, they require some alignment.
They're infuriating.
That
That was the issue with system I was hitting.
Oh, really?
It had to be 16 byte aligned.
Yeah. So before going through this, they align your pointer, but it doesn't matter. The point is, we managed to pass to this strlen. If we walk up the stack where printf calls strlen, or does it? If we look at our, no, yeah, of course, you can't do that. Anyways. The point is, we injected the value. Thank you very much. We have our value in the format string, and it's dereferenced as a read value with %s. So using that, you can leak memory and you can overwrite memory, right? So let's see what happens when print.c does this in a loop. All right. So now we're not going to drop into interactive because it'll just hang. So, or actually it won't hang because we're still going to crash it, right? It still crashed because it tried to read from unallocated memory no matter what loop it's going. But let's say we have this situation where print is running printf, the print library binary is running printf in a loop. We have, right now, we've disabled ASLR in this shell. Have we? Uh-oh, ASLR is on. Oh, damn it, I'm in the home. PIE is on. So what locations do we know in order to write stuff?
The offsets.
We know the offsets. So given the base address of the binary, yeah, we can, but we don't know any base addresses, right?
We can leak the base address using a format string.
Exactly. So we start out not knowing anything, but we can run this. Now, of course, it waits for input here. We can just leak stuff. And now we know where, looks like this is the format string itself. We know that, so that's the stack address. This then looks like it's going to be a libc address. This looks like a libc address. And now suddenly we know where libc is. So that's pretty cool.
Would you be like building rob chains with this, or is this like more of, is there going to be like a win function?
So this varies. So it's that situational. So with printf, as you can see, you can leak stuff, right? So now you know where libc is in this case. So now you could use printf with the %ns to write. When X is enabled, you saw that too in checksec. So what do? You can write a rob chain into the BSS of libc, and then overwrite or leak farther and figure out a return address on the stack. You can write your rob chain onto the stack and then trigger it by overriding the return address from whatever.
Right.
Yeah.
So we are going to be like kind of using rob chains with format strings. That's kind of like I'm trying to like look at the bigger picture.
Yeah,
Anyway,
yeah, exactly. So in the later levels of this one, maybe a little bit. Wrap chains, but also like, you know, redirecting to shelter initially, stuff like that. Initially, you're going to have to leak a win variable, not even a win function, right? In like level 0, like leak it off the stack. Then working up there, building a rock chain is probably something that we'll save for the Thanksgiving homework, probably, or starting to put things together. But maybe I'll throw it into the later levels of this. Some of that. But yes, that's exactly like the bigger picture. printf doesn't give you execution directly, right? You have to build something out of it.
Right.
Yeah.
Like move memory around until the memory works in the way that you want it to.
Exactly. Yeah. Yep. So let's get to this. So did I quit my IPython? Damn it. All right. So here's my IPython. We can leak. So we figured out the offset of our into format string here, but now we still don't know where anything is, right? So let's leak the stack. You can leak the stack by doing %lx that ljust 128 plus 2048. That's the full size of our format string. And actually, for our sanity's sake, let's make sure that this is justified. Do you see why I'm doing this? So that if I make a typo here or just leave it out altogether, it's not going to screw anything up. And then we do try format, and grab this leak. And now we have a stack address. Boom. Oh, and we used ASLR equals false. Highly recommend doing that because that makes the things a lot easier because you can see that that's a stack address. Cool. So let's figure out a libc address.
Wait, I didn't fully understand. What's the point of putting ASLR equals false? I didn't fully get that.
Oh. So if ASLR is not false, and of course eventually you have to deal with ASLR not being false. I run this multiple times, and every time this is different, right?
Oh,
so this is
yeah.
FF dead, this is FF EA16, and so forth. It's not the problem is that it's not a problem that is changing necessarily, even when you're developing this, if you're compensating for it. The problem might be like, can you tell with one glance if that's a libc address or if that's a stack address? Right?
Just leak some bytes out of that address.
Yeah, you can leak some bytes, but if you disable ASLR and you see that it's 7FFFF, then it's a stack address. So that's why it's one of the reasons it's easier. All right, so now we've leaked the stack. Let's grab a couple more things. I mean, what is this one? This looks like a library address. Why it now? Does anyone know why Pwn Tools? How does Pwn Tools disable ASLR? Is it not through setarch?
It does that setarch.
It does setarch?
99% sure.
So why does this end up at this weird address? Because I'm pretty sure that that is where, if we do the GDB on the core, where it crashed, if we do VM map.
That's in libc printf.
Yeah. But That's a weird address. How does Home Tools cause libc to be allocated at that weird address? That's
search.
You search that, but basically we leaked it out. We leaked out an address that seems to point this 1555553 is right here. Something in libc.
Would you expect those shared objects to be loaded?
Are 7FFF or 7FFF7. Well, we can check. Set arch x8664-r. Yeah. 7FFF 7F.
Nice.
And just other. Yeah, the 7FFF7. All right. Anyway, so we leaked a libc address. So now using our looped format string vulnerability, we can leak addresses like there's no tomorrow, right? So now we know where the stack is. We know where the libc is. Let's try to find our binary address. And with ASLR disable, of course, we know where that's going to be too. Scroll up here in our VM map. It's here, this 55555. So let's just keep going so we get lucky with this. 5, 7. Oh, that's a bunch of spaces. Might not be so lucky. So 1000. Nope. Oh wait. Oops. Oh, I see. I was changing the wrong. Okay, so that's 7. 6. Oh. Five, 4. Those are other addresses in libc. So we can do, for example, go everything up to 2000. Now we do this. We build our format string dynamically. And we run this, and it, what?
Oh, because 0? It needs to be +1.
Sorry. Here's what happened. It created this format string, %0 $LX, and injects it into the program. That's not a format string according to libc, because arguments in format strings in libc are 1 indexed. So it just printed that back to me. I grabbed it and I tried to convert it into a integer, and it didn't work. So we have to start our range at 1. And so now here we are printing out leaks at various offsets.
Why is it all 2020? 2020?
It's all 2020 because when we do ljust in Python, it justifies it with spaces. Yeah. So let's so it's actually very strange that it crashed here after 276.
Because you're not closing the...
Oh, because I'm not closing the things. So we probably ran out of file descriptors, as you can see from the thing. So here we can do r.close. And we keep running. See, now we're printing different stuff. And eventually we'll find one that starts with a 5.5. So let's short circuit this process a little bit. And we say if weird leak that starts with 5.5, break.
Weird leak is an integer.
You're right.
Also, wouldn't it start with OX 5.5?
Yeah, that's what I did. Boom. At 521, we have an address into the binary. Cool. So, at 521 $X. This is a no longer weird leak, it's a binary leak. Not all arguments converted during, yep, that's fine. And there's our binary leak. So now we have our binary, our libc, our stack address, and the offset into our format string. That 100 points to. You had a question?
Yeah, just out of curiosity, instead of doing all this, why don't you just GDB the binary, see where the first argument is, and then just stack 500 and just Control F?
Exactly. That's the smart, and so that's what we did earlier, right? To figure out the offset into our format string on the stack, right? You can do the same for any of these other things. I don't know. As you can see, sometimes I like brute forcing rather than thinking. You can do it either way. Honestly, that method's probably better. Okay, one thing I want to draw attention to with ASLR off. This is fine and dandy, right? What happens if I turn ASLR on? First of all, it won't always be 5.5, but we figured out the offset with ASLR on, and now we have this 521 offset. So even if you turn on ASLR, let's do it.
Start.
Yeah, here it is. So
as long as you're not reading across segments, ASLR shouldn't matter for that, right?
for that, yes. But what's wrong with this picture now? So we turned ASLR off, on. We ran it. It told us, okay, hey, the format string is 624. That doesn't change with ASLR. ASLR just ships where the stack starts. No problem. Your stack address is actually, hold on one second. Yeah, your stack address is somewhere. Fine, that's the stack address. Your libc address is here. That's fine too. No problem. Binary leak. What's wrong with this? You moved your hand. Accident?
No. I don't know.
No, not you, Matt. Just scratch it. Be careful. I'll tell you what's wrong with this picture. Each time we are probing with this format string, we launch the binary. What happens when you launch the binary? It re-randomizes. So this is static because it's just a relative offset on the stack. This is the stack address for this execution of the binary, PID 24894. This is the libc address for this execution, 24895. It no longer has the stack address that we leaked earlier, right? That's not a problem. We can do all of this in one fell swoop. So if we do LX for the stack address, then 4LX for the libc leak, then 521 LX for the binary leak, $. We try the format, and then we say the stack leak, the libc. Let's yes. So let's read the line.
You should put something like a pipe at the end, just so you can split on that. That's what I normally do.
Like between here?
Like just after that X, after the last
Oh,
X.
but you can split on spaces.
Right, but it's just very easy because it's going to justify the spaces.
Yeah, but check it out. What we do is we do the first three. And then, so this is our output. This is our stack string, our libc string, and our bin string, and then we stack leak libc. Stack leak is int stack stir 16. Libc stir leak is int libc stir 16, and
why are you converting them to numbers?
Oh, for adding stuff later, if you want to add offsets and calculate addresses of stuff. And then we have this aim. So here I was printing out the wrong thing. Let's see. Boom. So in one process, PID 25698, we have the stack, the libc, and the binary. Cool. So now, when we can do a printf again, we'll actually be able to overwrite things intelligently and target things intelligently. So, let's see. What should we do next? Next, let's, now that we've leaked the binary, let's add a win function in there. And we will jump to the win function. We'll override the return address with a win function. We'll call it a day. Cool? Cool. Wow. Okay. So,
the binary though is like all those values will change or need to change.
I'm sorry?
I said by adding a win function, is it going to change where C is at and all that stuff's at?
It'll change where stuff is inside within the binary, right? So like if we had already calculated the offset of something in the binary, the BSS won't change. But offsets within the binary, that'll change. But it won't change. ASLRs will change is where the binary is placed.
Yeah.
It won't change that.
So I'm saying the format string, is it not going to change where it is for the, okay.
That's all stack relative stuff.
Okay.
Yeah. So let's add a win function. And what does win do? Win does open /flag. And then it'll do send file to 1 from flag 0 24, right? Or is it 0 0 10 24? 0 10 24. Okay, and that's it. All right, let's recompile that. Make sure that our leaks still low. Make sure that our leaks still work. Everything is good. We have our binary leak. So let's see what is add the binary in this 1897. Aha. It's a return address. It's the return address from bar into foo. Right? So now we know that we have the binary leak, so we have the binary base is bin leak minus OX 897. So let's see where the win function is. 7DA. Now we print okay, that's the address of our win function. So what's left?
Insert it into RSP.
insert it into the stack where the return happens, right? Overwrite the return address. So, what return address do we overwrite? We overwrite we know what return address. So, like before, we have our binary leak, and our binary leak turned out to be the return address. We're leaking this binary address from the stack, right? By seeking farther into the format string. And specifically at a distance of 521 64-bit words, right? So farther down to the right in the stack, we find our return address to foo from bar. That's exactly what we want to overwrite, right? With our value. And specifically, actually, all that we really need to overwrite is the last byte of it, or the last 2 bytes, to go from 897 to 7DA. Do you agree with me? Yeah. So it's even a little easier than overwriting the whole thing. So what's left is to figure out where on the stack exactly, in absolute terms, that address is, so that we can write that address into our format string and use it for the %n dereference. Okay? So let's do it. We have our stack address, and we have the address that the return address, the offset that we want to overwrite. Figuring out the exact relationship is a pain in the ass. Let's do it in GDB. So we do GDB print. And let's break at printf. Let's print an example format string for us here. So where's our format string? So we'll run. Actually, let's write that to the. Cool. All right. So now we run with fjust. What? Oh, format. Sorry. We run with format. Okay, we're in printf. We leak the first address to get the libc leak, right? That's the. What is that? That first argument, RSI. Semantically, what does it mean? The second argument. And I guess that's a trick question. Semantically, it doesn't mean anything in this context. It wasn't meant to be passed into printf, right? It just, whatever happened to be in RSI before, it happened to be a stack leak. Let's see what it is. XGX RSI. What? Oh, sorry. Okay. Yeah, SLR is off in this one. Okay, no, it's correct. Here it is. You're right. SLR is off here. It's on here, and it ends in 0C0, and this ends in C0, and everyone's happy. Interestingly, RDI and RSI happen to be the same thing, and they are both our format string. That's our format string. So I don't know why they happen to be pointing to the same thing right now. Like I said, RSI. Oh. Why is RSI pointing at our format string?
Because it's taking another address. running, so we are passing 3 arguments, so it's looking for the other 3 arguments.
Here is our source code. Zach.
Read.
The read. What was passed as the second argument to read? The format. So that gets put into RSI. Read runs. It stays in RSI. RSI is a callee saved register. That means that the contract that the functions have with each other is that they will not clobber, or they will restore RSI to whatever it was at the beginning of the function when they return. So RSI survives read and then runs into printf. And so RSI is the format string as well. Anyways, the point is we have our format string, and we should be able to actually very easily figure out the offset. So it's 4096 is the stack size of bar, and then after that is the return address. Probably some padding, definitely a canary, but somewhere right around there, 4096 divided by 8, plus or minus a couple of things, which actually makes sense. That's our 521. Right, so let's actually look. 4096 divided by 8. You're right. Is 512. There's probably some padding involved. Plus 6 for the 5 register arguments. So let's say plus 6. And this makes sense. We're within plus 1 for the canary. Plus 1 for the base pointer. Whoops. And then probably plus 1 for padding. And that's our address. Anyways, so that's nice and simple. Let's get back into GDB. We have an hour and 10. Oh, fuck.
0 minutes. Actually, class is over 5 minutes.
Class is over.
Wait, class is over at 8:45?
It's always over. Yeah.
It's over at 8:50, not at 9?
No, it's 8.
I've been holding you guys over.
Every year.
All right, real quick. Wait. All
Don't you remember Adam yelling at you about this?
right. Yeah, but
Wait, let's get the flags.
let's get the flag. Okay. So
I do have to go now.
yeah, here's RSI. It's pointing to our thing. If you look at this plus 4096, whatever, that's 1. Who knows why that's 1? That looks like a canary value. Why do you think it's a canary value? Or why did you think? 0, 0, and a bunch of random shit. So here's 16. Oops, wrong one. 16. That looks like a saved base pointer. 24. That is our return address. Ends in 897. Ends in 897. Right? So basically, we take our stack leak and we add 4096 plus 24, and that's our target. Right? So let's confirm this with ASLR. Oh, the stack won't line up, so it's fine. So here's the win function address. Here is return add pointer target. I'm sorry?
We need an indirection pointer for that.
That is our indirection. That will be our indirection pointer. So that's what we'll dereference with %n to overwrite the return address. So let's run this. B38. And this is CD8. That's not. Oh, wait. Oh, this alignment changes. An interesting fact about ASLR that you'll run into, especially with this, is that, and I found out about this recently, ASLR puts a bunch of shit on the stack. It's insane. I had no idea.
That's pretty smart.
Yeah. So yeah, if you want to, you can run it outside of ASLR to be more reasonable. So this is going to be complicated with this stack massaging, not here, but in general for the homework, because ASLR puts shit on the stack.
What do you mean by
GDB, huh?
that? What do you mean by that?
it literally puts a bunch of, it shifts the stack pointer before hitting your program. So you have the environment, and then a bunch of zeros, and then you run.
Right, but it doesn't like randomly make data.
Correct. It doesn't randomly make data. It shifts the stack. I'm sorry?
Is that so ASLR free homework?
No. All right. So we have the return address. So now we can actually create a format string that will overwrite that return address with something. So we say format is send $100 $n HN. We want to overwrite 2 bytes. Yeah. Because there's the 2 bytes, we want to go from 897 to 7DA. Right? We're going to adjust that to 128 plus we're going to A times the format offset. And now we do pwn.p64, our address. So let's make it here. Okay, our address, and that's it. And then the rest is nonsense. But what do we want to write to that address? We want to write OX7DA, right? To the bottom 2 bytes. Let's see what OX7DA is. And that's 2010. So %n will write the amount of bytes that we've written so far into that pointer. So we have to make printf print 2010 bytes before hitting it, and that's very easy. We do %2010C. It'll print 1 character padded to 2010 bytes. And then when %n hits, it'll print 2010, which in hex is 7DA, which is our win function. And now, whoops. And now we do r equals try. So this is pwn format. Try format. Pwn format. And r.interactive. Let's run it. Whoops. I'm sorry? Oh. Okay, something weird happened here. And it crashed. Do I have a flag? I do have a flag. Okay. So, why might it not work? Let's make sure it dumped the core, and then we can see. Yes. Okay. So it crashed. Here's that core. And it crashed in 55507DA. How cool is that?
Nice.
We rewrote the return address to exactly what we meant to rewrite it to, but why did it crash? I'm sorry? Exactly. It's not 07DA, it's something 7DA. And I am currently running it without ASLR. So if I'm wrong once, I'll always be wrong. If I run it with ASLR, I'll eventually be right. So I'm just going to print this.
Is it going to still be 07DA?
It will be, but at some point, ASLR
will be 07DA,
yeah, exactly. So we run it on average 16 times.
I always found A to be a very good one.
Won't ASLR shift your stack and make this not work all over again?
Where he's writing.
Because you said it puts a bunch of stuff.
It does put a bunch of stuff, but all of this is relative on the stack.
All right.
The location, so he's writing the stack that points to the return.
Come on. Come on. Okay.
I feel like
Let's turn ASLR back on, ASLR back off, and I will just do 4i in range 16. We will just add this instead of red adder. We will do plus. No, wait.
I times 0 and 1.
Yeah, I times 1.
Sorry, not.
No. So the offset of the so if you did percent n offset, it works fine if you just add items overwrite percent n dereferences writes your document.
Okay. So now we're just going to try all of them, and one of these should have the stack for it. Or the stack there. No? What? No. Something is wrong. Oh, hold on. It's crashing at the right.
Whatever. It's not saying, it's not like it's writing.
Look at this. This is no good. You have a bunch of A's where there shouldn't be a bunch of A's. Yeah, that's probably a good idea. Well, the problem is we need to get the alignment correct. Right?
Well, that's what I'm saying. You can just print the address over and over again and get the alignment. Right?
Sorry. Okay, I found it. Here. I was justifying the wrong thing for the wrong amount.
I see, like that.
You can still do that, and then
exactly.
do like a for loop of 8 times to see which one gets the correct one.
Yeah.
But yeah.
Turn off all that.
No. The fuck?
No. He has ASLR.
Okay, let's turn ASLR back on. Oh, I wasn't printing the return. So, I turned ASLR back on, and I'm going to do this 100 times.
Hey, Jan?
What's up?
If you turned ASLR back on, does it mean the return address changed? The one that you're hard putting in?
I didn't hard code it.
You didn't hard code. He's using offsets.
No, red adder. Right, but you're invoking it twice, right?
Oh, fuck. Thank you. Yes. Multiple things have gone wrong. Instead of this, the thing reads the format string in a loop, so we're just going to do send line, phone format. That I'll just 2048. And then print r.readall.
Wait, is the program just waiting for input though? Because I don't think that's the case.
The program should be waiting for input.
It's not waiting for 100 inputs. It's waiting for one input.
So it.
You need to. You want to spawn it 100 times, right?
Yes, you're right. This is what it's doing. It's doing while one do foo, which calls bar, which calls the print.
If you get the return address wrong, it's going to crash.
Yes, you're right. So here, I should do the whole thing 100 times. Boom! All right. into a file, and I'll email it out to you.
Does this mean that after 3 hours we finally done level 1?
Yes, this means after 3 hours we finally did level 1.
And look, we're out an hour early. Clock says.
And we're out an hour early. 45 minutes.
I scheduled a meeting like you said. What am I having a meeting about?
Just to meet with us, talk about potential projects.
Okay.
What we'll probably do actually is have like a session with everyone in the lab, like next week sometime.
I
like
picked tomorrow morning.
Yes. That's good.
Okay.
And then we'll meet you, and then the week after, we will have a meeting with everybody, so that
anybody in RPX that goes to